I mean, how can you expect to do it, well on an exam if you can't do the problem sets, right? So they're important. I just hate grading them. Okay? Everybody? All right. Okay. Let's see. Okay, I'm ready. All right, let's review. So this is the equation we're going to use for all of these continuous charge distributions. So all we're really doing is we're calculating the E field of a point, and then we're just summing them. That's all we're doing, just summing the E field of a point. But the E field of a point is a vector, so that means it's a mess, right? It's not trivial, okay? All right, so the E field of a point, so we're calling the point dq, so the E field of a point, we're going to call it dE. It's just k dq over r squared, just k q over r squared, And again, this is what we did yesterday. So we wanted the E field here, so we just added up all these E fields. Okay, so when you look at this, you realize, golly, I want either a dx or a dy, so I have to get rid of the dq. The way you do that is by using these charge densities. So we used this Wednesday. I keep saying yesterday. Wednesday. We're going to use this today. And they're always constant. If they weren't constant, we'd be up a creek, all right, without a paddle. So for like yesterday, the linear charge density was total charge over total length. But if it's uniform, which it's always going to be, then the total charge over the total length is the little charge over the little length. So therefore, dq is just lambda dy. Bingo. So there we go, right? So, all right. So that's how you substitute for the dq. And then r squared, sometimes you have to substitute, sometimes you don't. It depends if the variable is in there. I think we're going to have one today where you don't. Yes, okay. All right, so I discussed the dq, I discussed the r squared. Now again, it's a vector. So you have to write dE as a vector. And then you want to see, okay, maybe I'll be able to eliminate some of these. So Wednesday's problem, we were able to eliminate this one and this one. And so don't forget, it's a vector, all right? Don't forget, it's a vector.
Does it even have a Z?
No. Yeah, we're pretty much going to stick to 2 dimensions. Keep it easy, right? But like I said, Wednesday, I think you'll have it. I think this is we're either going to do this in class or a homework. I just don't remember. No, in class, that's right. So we're going to do this in class. This is a charged wire, but it's an arc. And so, the E field is going to be like that. So you can have an X component as well as a Y component, right? You can't eliminate either of them. Okay. Okay, so we have 4 that we want to do, 4 problems we want to do. We've done this one, no kidding. We did this one Wednesday. Today we're going to work on this one. And this is going to be a no-brainer. So I'm going to do this one. Sorry, guys, you have to watch. But the next one, which is that one, the arc, you're going to do by yourselves. So basically I'm going to describe it. And I'm going to say, have fun, and I'm going to walk out. And I'll give you 15 or whatever minutes to do it. Okay? So pay attention, because you're doing it on your own. But this is going to take us a long time. So let's do it. Okay, so here's a question for you. So here's a puzzle. And let's say that each person pulls on each segment of the puzzle with the same force. Okay? What's the net force on the puzzle? 0. Now what does that have to do with anything? A lot. So just keep that in your head. All right? Okay, so here we go. So the first thing we're going to do is we're going to do a ring of charge. Like I told you Wednesday, we want to get an infinite plane. So we're going to start off with a ring. Then we're going to get a disk, and then we're going to get an infinite plane. So that's the steps, okay? So 3 steps. Ring, disk, infinite plane, all right? All right, so you ready? Let's do it. So we want to find So it's basically a charged wire, right? It's a charged wire on the table, and we want to know the E field right here at point P, okay? So you just imagine, you know, here's all these little point charges, and the E field points like this, right? All these E fields point up. Well, I mean, at some angle, you know? All right? So what is going to be the direction of the net E field at point P? You should think about this. What's the answer? What's going to be the net? Straight up, right? Because what's going to happen to all, like what's going to happen to this one? Yeah, how come you don't have anything with at an angle? Because they're all going to cancel. Now do you see why I showed you that? Okay, all right. So all of the E fields along the, let's call this the XY plane, you know, the horizontal plane, are going to cancel. So all we're going to have left is the Z component. Is that super crystal clear? Any questions? Okay. All right, so let's just go through our, you know, so, okay, so so the answer is going to be, so E is going to be in the K hat direction, right? Okay. Now, what's given? So what do we know? What's given? In other words, what our answer can only contain at most the stuff that's given, right? So it's given. Okay, the radius of the wire. What else? How about, yeah, the Z, right? The distance from the horizontal plane to the point P, right? I mean, you're right, Katie. Right? But, I mean, little r squared, just big R squared plus, you know, little Z squared. Okay, what else? Come on, something super basic. What's true about the ring? It has a charge. Q! Right? Okay. So, at most, our answer can only contain big R, little z, big Q, and physical constants. If it has something else, it's wrong. Okay, so step number one. If you look at your handout from the other day, step number one, consider the object and nothing else. So all you're looking at is the circular wire, all right? Don't look at all this junk above it. Just look at the circular wire. And there's all these point charges along the circular wire. So we have to choose a variable, right? We have to choose a variable that describes the position of the point charges. So it's a circle. So what would be a good variable to describe the position of a point charge on a circle? Sorry? No, I just didn't hear you. I mean, you know, so the other day we had a wire like this. And we said, why, right? Y would be a good variable to designate the location of a point charge. Now we have a circle, well, you know, a circle. So do we want to use X and Y? No. Oh my gosh, that'd be horrible. Well, look at the picture. So what do you think we should use? R. Okay, let me give you a hint. Okay. How about S? The arc length. Right? S? You know? I mean, you know, we'll say that this is like, you know, we have to have some kind of a reference point. Like this, we'll say that this is S equals 0. And then, you know, we'll just say, so S goes from 0 to 2 pi r, right? Okay. All right? So what I wanted you to do is look at this and recognize, hey, there's a ds there. That must mean that the variable is s. Okay?
I saw that, but I was afraid of sounding stupid.
Come on, there's only
So intelligent.
there's only 5 of us. You don't have to worry about sounding stupid.
But it is being video.
6 of us. That's true. It'd be on tape forever. People from all over the world. You know, so during the pandemic, the 2020, I actually got an email from somebody in, where was it? Some far-off country, like someplace in Europe or something like that. This woman was in college taking physics, and she found my slides, and she really liked them. Can you believe it? Because I put them open to everybody. I make them public. So anyway, that really cracked me up, right? Okay, so S is going to be our variable. Okay, S is the variable. All right, now, look at the equation. We have to always substitute for dq, correct? All right, let's do it. Okay, so this is a linear, well, you know, it's a wire, right? It doesn't have any thickness. So we're going to use lambda. So lambda is the total charge over the total length. All right, what's the total charge of that thing?
2.
What's the total length of that thing? What's the total length of a wire with radius r? 2 pi r, right? The circumference, 2 pi r. Right? Okay, now, the linear charge density is uniform. So this is the total charge over the total length. So that's equal to what?
Little charge over little length.
Yeah, the little charge over the little length. And again, see, ds, right? Because that's why we chose the variable. So again, this is uniform. Total charge, total distance, little charge, little distance. That's what it means to have uniform charge density. So therefore, dq equals lambda ds. Ta-da! And that's exactly what you expect, right? Because that's why we do this lambda thing, because we want to get dq in terms of our variable, you know? Okay, so later on, you know, we'll take care of the lambda equals q over 2 pi r, but I'm not going to worry about it now. It's too much writing, right? Okay? All right. Okay, so that's step 2. Okay, step 3. What's step 3? We did the dq. Again, what you should really focus on is that equation. So we did the dq. What's our next thing? R squared. Okay, now look. Does r squared vary, or is it constant when you go around the wire? It's constant. Isn't that great? So we don't have to worry about it. Yeah, I know. I mean, remember how yesterday Wednesday it wasn't constant, so it was kind of a big deal. Okay, but, you know, we should really write this in terms of the given. So let's just say that r squared is big R squared plus little z squared, okay? I might just use this for a while, but then eventually I want to use this, right? Because we want our answer to be in terms of what's given. Okay, that's fine. Okay, what's our fourth step? Components. Okay, so dE equals dEx plus dEy plus dEz. Okay, what can we kill? X and Y. Isn't that awesome? Okay, so great. So look at the picture. What's the magnitude of dEz? According to the picture, what is the magnitude of DEZ? Everybody agree? Somebody else ought to answer questions besides Katie, by the way. Come on! dE cosine theta. Now, this is true, but again, I want my results in terms of the given information. So what's cosine theta? So if it were me, you know, I would look down here, look at this triangle. So what's cosine theta? Somebody else besides Katie. What's cosine theta? Z over, remember, cosine is adjacent over hypotenuse, right? So what is it? Yeah. So we have dE, then we have Z over little r.
I'm confused at why we know Z and big R, but we don't know like theta.
Well, we do know theta. But I mean, all I'm saying is, this is how the problem was going to be stated. They're going to say, you have a charged ring of radius uppercase R. You want to know the E field Z away from the midpoint of the circle. You know? So, I mean, so they're going to give us big R, they're going to give us little z. So you're right, we could figure out little r, we could figure out theta, right? But I'm just saying, you know, they would give us the radius of the ring, and they would tell us how far above the horizontal plane we are. Okay? We don't want to have to, yeah. Okay. But yeah, you're right. Okay, so there you go. Okay, so what's our fifth step? I mean, is there anything else that we have to substitute for? So what do we do now? Just put it all together, right? Just put it all together. I might be having my numbers wrong, different, but that's okay. Okay, so this is what we want to sum, right? We want to sum all the DEZs, okay? So let's do it. All right, so DEZ is DE, I'm not going to skip any steps, times Z over R. Okay, now what's DE? This is an easy question. What's DE? What's the E field of a point charge? Yeah, I mean, seriously, that's what it is, right? Okay, so don't forget, DE is just it's an E field of a point charge, where the point charge is dq. So DE is just k dq over r squared. All right, that's the DE, okay? And then I have my z over r. Again, I'm right. Okay, so far so good? Okay, and then I don't like my dq, so I have to substitute for that, right? So where's that? Over here. So dq is lambda ds. So I have k lambda ds. I'm going to put my z here. Is that all right? So I have k z lambda ds over r cubed. All right? Everybody happy? Any questions? Okay. And I guess you don't have to do this, but I'm just going to pull out the ds. I just want to make it super obvious that that's what we're going to be integrating. You know, you don't have to. All right. So that wasn't too bad. The only substitution we had to do was the dq. That wasn't so bad. Well, that's not totally true. I mean, we had to do all this component things too. All right. Now that's the magnitude, correct? So now we want to, okay, so now we have the total E is the sum of the little fellas, right? Which is, and that's why I like writing it like that, which is this k z lambda over r cubed integral ds. Now, that's it, right? I don't even have any s's here. How much nicer can you be, you know? Okay, so what are my limits of integration? 0, okay, then it has to be a distance, right? 0 to what? Okay, so here's a circle. So pretend we're looking down on it. Here's a circle. I'm going to call that s equals 0. And I'm going to go all the way around. 2 pi r, right? Because it's a distance, right? 2 pi is an angle. 2 pi r is a distance, right? Okay. So yeah, just look at those units. Remember, I keep saying units are your friend. Okay, so 0 to 2 pi r. Wow! What's the integral of ds from 0 to 2 pi r? What's the integral of dx? What's the integral of dx?
X.
X. What's the integral? Okay. So what's the integral of dx from 0 to 1?
1.
Okay, because it's integral of dx is 1, right? But integral of dx is x, but then I go from 0 to 1, so that's 1 minus 0, which is 1, right?
That, yes, I'm following.
Okay, so what's the integral of ds? What's the integral of ds? S, and s goes from 0 to 2 pi r, so what is it?
1.
Okay, kz lambda over r cubed, right? That's all constant, right? And then integral of ds is s. But we're going from 0 to 2 pi r. So therefore, I have kz lambda over r cubed times what? 2 pi r minus 0, right? Remember? You guys are forgetting your first semester calculus. But does that make sense? Remember? Oh, you did? Okay. All right, is everybody, all right, so basically the answer is k's, okay, wait. Sorry, Adam. Okay, so it's just 2 pi r, right? Okay, so what do you say? We should probably put in our lambda now, you know? Okay, so we have kz over r cubed, put in our lambda. Where's our lambda anyway? Where is it? Lambda is q over 2 pi r. And then we have 2 pi r. All right, so goodbye. So we have kzq over little r cubed. And again, I think we should really write this as kzq over, oh golly, r squared plus z squared, 3 halves pi r. And then we want to make it ta-da. Okay? Okay, so I wanted to substitute this just because, I wanted my answer to be in terms of givens. Okay, so everybody please look at this and tell me if there's anything you don't understand. And it's okay to ask. Any questions at all? Please ask. Any questions? Adam, you look like you can ask a question.
No, I'm just trying to follow the math.
Okay.
On step 4, second one, can you talk?
This one here?
Yeah, like how you went from
Okay, so you look at the picture. So this is DE. This is DEZ, right? So isn't this is adjacent, so it's cosine.
Oh, yes.
Right? Okay. And then you look here, so cosine is adjacent over hypotenuse, which is z over little r. Okay. Okay, other questions? I'm glad you're asking. Just some little crazy thing like that will make it challenging, So ask questions. Any other questions? Everybody all right? Okay. All right, so let's see if it makes sense. Okay, so is the answer in terms of big R, little z, big Q in physical constants? At most. You know, it might not be, but I mean, it can't have anything else. Okay, so we passed that test. Okay, now we want to, okay, so here's the circular wire. Let's say we go up to outer space. What does a circular wire look like?
Small.
Like a point, right? Okay, so let's write KZ. Okay, so that's what it is, correct? All right, now, how can we, so we want to check if the thing, you know, if it reduces to a point charge when we're far away. But mathematically, how do we say we're far away? What has to be big, what has to be bigger than what? Yeah, right? So what we want is Z to be tons bigger than the radius of the circle. Okay? All right, so you always divide by the thing that's big. So here we divide by r squared, divide by r squared. Now to compensate for that, what are we going to multiply it by?
Wait, isn't Z bigger?
Oh, sorry. Golly. I'm glad somebody's paying attention. Just kidding. Okay, what are we going to multiply it by? Come on. What do we have to, I mean, I divided by z squared inside here, but I can't just go dividing by z squared, right? I have to multiply by something to. Cubed, right? Cubed. Because here's a z squared to the 3 halves. What's a z squared to the 3 halves? Z cubed, right? So I have a z cubed, so, right? Because, I mean, so this is a z squared to the 3 halves power on the bottom here. Well, that's a z cubed. So if I, right? So that means I have to multiply by z cubed to compensate for it. Okay? All right. Now, let's do what we always do. So z is tons bigger than r. Okay, so what's z squared over z squared? 1. What's r squared over z squared? 0. What's 0 plus 1? What's 1 to the 3 halves? So I have a z cubed on the bottom, right? So I have a z cubed on the bottom, but what I have a z up top. So that's just going to be kq over z squared. Woohoo! That's what we wanted, right? The E field of a point charge. Okay? Now again, this doesn't prove our answer is right, but if this didn't work, we know we know we're wrong. Okay? All right. Awesome. What should the E field be at z equals 0? I mean, just by looking at it. You know, you have a circle with all these point charges everywhere. What should the E field be right there? 0, right? You know, because like if they're positive, they're all going to point like this, and they're all going to cancel each other, right? Okay. Well, what is the E field at z equals 0? 0. Okay, all right? Okay. So all I'm saying, you know, when you get an answer that's kind of messy, you should just kind of run through and see if it makes sense. Okay? Do it far away, do it close, you know. Okay, all right. All right, that was cool. Okay, so that's nice. Now what we have to do is we have to use that result for a ring or a wire to get a disk. So how can we do that? All we know is the E field of a wire. How can we use the E field of a, how can we make a disk out of a wire?
Wait.
Well, now remember, integration means adding, right?
So add a bunch of rings together?
Yeah, basically, right? So basically what we're going to do, you know, we're going to have so here's our disk, and here's our ring. We're just going to keep adding rings that are really close to one another, right? In other words, we're going to integrate from here to here.
Okay.
So we're just going to add a whole bunch of rings. All right? Okay? Just keep adding those rings until we have a whole disk. Pretty good idea. So let's do that. Oh boy. You know what? It's on Canvas. I'm not joking. No, but I mean, I gave you a handout yesterday or Wednesday. So I also have a handout for this, and it's on Canvas. So if you miss something, yeah, you can just go to Canvas. It's there. Okay. All right. So look, we're going to say now that the ring has width dr. So it's really small, right? But it's not 0, you know. And then like everybody just said, we're just going to keep adding them together. All right? Now, one little thing that's going to be different. The disk is a two-dimensional object, right? So, we can't just say lambda equals dq over dl or something like that. All right? Because now we're going to use that eta. So eta is a charge over the area. All right? Okay. So Q over area. Okay, so if eta, which is the charge per area, is the total charge over the total area, that's also equal to the what? Yeah, so it's equal to dq over dA. All right? Now that's important, okay? Total charge, total area, little charge, little area. But now the little charge is the charge of the whole of the wire, Okay? Look at the picture, Okay. Now, in the old, with our previous result, we just had dq over ds or dy or something like that. It wasn't anything big. But hold it, what's a dA? Because remember, I'm going to solve for eta now. I mean, I got to get rid of my dq. So I'm going to have dq equals eta times dA. That means I got to integrate, right? So I'm going to have dq equals lambda dA. Well, what is that? How am I supposed to integrate that? Because the dq is going to be my integral, right? So how am I going to deal with that? I want a dx or a dy or d something. I don't want a dA. Sorry? So I got to substitute. So I'll show you two ways to do it. Okay, so what is dA? It's the area of the wire. It's the area of the wire. So what is the area of the wire? So in other words, what's the area of this? Now remember, it's supposed to be infinite. It's supposed to be really small, but anyway. Okay, 2 pi r times, so that's this, times what? What's the area of a rectangle? Length times width. Okay, this is the length, right? The 2 pi r. What's the width? dr. Okay? Okay, so number one, the dA is the circumference times the thickness, which is 2 pi, by the way, small r, right? Small r, agree? For the wire, small r. So it's 2 pi r times dr, okay? All right, does that make sense? Okay. Here's a second way to do it. Okay, what's the area of a circle? Yeah. So the area of a circle is pi r squared, right? Okay. what is dA dr? What is it? 2 pi r. That means that dA is 2 pi r times dr, right? So either way, you know, I think this is the way, I don't know. I kind of like this way because you kind of see it. This one, that's just okay, but whatever you like, all right? Whatever you like. Okay, awesome. Now, oh boy. I can't believe it, I erased it. Okay, that was a big mistake. Okay, hold on, I got to write down the answer for the other one. So what we had for the ring was E equals K, Q, Z, R. What? Oh, good, thank you. Thank you. All right. So now what we have to do is use that. Okay, so we have E equals the sum of the little fellas, which is the sum. Okay, now, for the Q up there, what are we going to use? Because remember, that's the charge. The Q was the charge of the wire, right? Well, what are we saying the charge of the wire is now? Sorry? Just look at the picture. What are we saying is the charge of the wire? dQ, right? Okay. Also, what was uppercase R in our answer? The radius of the wire. Well, what's the radius of the wire now? Small r. And it's going to go from what to what when we integrate? It's going to go from 0 to big R. Okay? All right. So we can do it. Okay, so we have K dQz, right? So we have K, I'm just going to write KZ dQ. I'm just writing that. Don't worry. R squared plus Z squared to the 3/2. Okay? So far, so good? I've just substituted dQ for Q and little r for big R. But now, what is big dQ? That's okay. What's dQ? I'm sorry, I wrote little q's and big Q's. Hope you don't mind. It's the same thing, right? Okay, so maybe I should just do this. Sorry. Then it won't look so bad. Okay, big dQ is lambda dA. So I have kz lambda dA over r squared plus z squared to 3/2 power. Okay, yeah? I mean eta, gosh. Thank you. So I put it over here. Golly. You guys gotta, I'm glad you guys are catching on. I mean, you're paying attention. Okay, then I have integral k z eta. Okay, what's dA? This thing, right? 2 pi r dr. 2 pi r dr over r squared plus z squared to the 3/2 power. Oh my goodness gracious. Okay, what can I pull out of the integral? What else? What else? Okay, what can't I pull out of the integral on the top here? R and dr, right? Okay, so I can say 2 pi kz eta integral r dr over r squared plus z squared to 3/2 power. Right? And what are my integration limits? Now you got to be careful. Little r is the variable. So what are my integration limits? From what to what? Yeah, 0 to big R. Okay? Okay, any questions? All right. So I'm going to, we could do this, right? By use substitution, right? Because we have an r squared here and we have an r here. So we could do it with use substitution. You guys, I'm not going to do it because we're running out of time. But you make sure you can do it, okay? Please. Say u is r squared plus z squared du equals 2r dr, right? Make the substitution, all that stuff. Remember you learned how to do that in calculus? Okay. You did. All right, so here's the answer. 2 pi k eta 1 minus z over r squared plus z squared to the 3/2 power, to the 1/2 power, sorry. Okay, that's the answer. So please, you guys, go home, do this, and make sure you can go from here to here. I mean, you got to know how to do that. All right? Okay, so there it is. That is the E field of a charged disk. All right, now we want to get an infinite sheet out of this, right? An infinite plane. How long do you think it's going to take us to do that? 2 seconds. 2 seconds. Okay, what do I want? If I want this thing to be an infinite plane, what's going to be bigger? I mean, what am I going to say? What is bigger than what? And here's a little hint. Here's my disk, okay? What does a disk look like if I'm, this far from it?
A point. No. Oh, big.
Okay, so what is bigger than what?
Big R is bigger than
Big R is tons bigger than Z, right? Everybody agree? Okay, so look, life is so good. If big R is tons, so what is this going to be? We don't have to do all that fancy stuff that I always do. Just look at it. If big R is tons bigger than Z, what is this fraction going to be? 0. So therefore, what's the answer? 2 pi k eta. Now, give me 30 more seconds. Okay, so we have E 2 pi k eta. Now, remember I told you that once in a while you're going to have to know what k was or is? Right? So who knows? K is what?
1/4 pi epsilon.
Right, 1 over 4 pi epsilon naught. Let's do it. So we have 2 pi eta. So we have 2 pi eta times 1 over 4 pi epsilon 0. You don't have to do this, by the way, but everybody does. So what do you notice? That cancels. So the 2 pi and the 4 pi, we just get a 2. So we just have an eta over 2 epsilon 0. Whoa! Now, what's this thing, a variable or a constant? What's this thing, a variable or a constant? It's a constant. So guess what? The E field of an infinite plane is constant. Just eta over 2 epsilon 0 is constant. And that's going to be incredibly important for real life applications, which we will talk about next Wednesday. Okay? Now, I hope you guys are super impressed. I mean, this was a total mess, right? There was a lot of work, And then we get this incredibly beautiful answer. I mean, it's incredible, All right, thank you very much.
I realize this is a little while away before the lab. When we get to it, are we gonna stay upstairs? Or
Yeah.
Okay.
No, downstairs.
Or downstairs?
So this is a one-time thing?
Oh, no, we're going to have class in here from now on.
Okay.
Yeah, class in here from now on, but lab is going to be down there. Okay, so this is awesome. Uniform E field. Oh, we're done. Oh, sorry.